Hi, this is Rob Sin, and this is covering the first section of my geometry course, Math 3120. We're going to be talking about the foundations of geometry, and we're going to be using finite geometries to illustrate that. So this is the online course notes, and I'll just tell you that we're working on this key idea here, that this course is designed not just for high school teachers, but it's designed to be useful for high school teachers. So the main axiom list, there's several lists of axioms that generate Euclidean geometry, but the main axiom list we're going to use is the School Science and Mathematics Group, SMSG, axioms. And the problem is that very few textbooks that start there, because they're at the high school level, are rigorous enough that they prove everything from first principles, and you end up with a lot of key terms undefined, and they're not actually established thoroughly. There are lots of more rigorous textbooks, but they're usually used for college geometry courses, and they typically do not start with the SMSG. They start with some other set of axioms, perhaps those by Hilbert um, or or Birkhoff even. So what I've done with these course notes is I've gone in and developed a set of notes where we start with the SMSG, but we still build all the rigor that we need. So let's start talking about formal axiomatics. What does it mean? So if you think about the Pythagorean theorem, mathematicians don't claim it's true always. We know that the Pythagorean theorem is true in plane geometry and Euclidean geometry. As a matter of fact, it's not true in other geometries. So mathematicians are looking for a set of axioms, right? A set of undefined principles that we're going to believe are true. We're not going to prove them, we're going to assert them as true. So with formal axiomatics, um, we have several things that we need. The first are these undefined terms. So even with our definitions, we have trouble because you have to use some words to define other words, right? Well, so we're going to start with undefined terms. And in most geometry, point, line, and on or intersect, these are undefined terms. We're just going to let them develop meaning as they're used in the axioms. So that's what I mean by undefined terms. We will never define them. They're terms that we're going to use, and they do have meaning, but we're not giving them formal definitions. Okay. The next set of things that we have are defined terms. Now, these are things that we're actually defining. This, for us, is going to be ideas like parallel or perpendicular, right? That we can create those definitions and talk about points and lines and how they intersect. So they can be based on the axioms and the undefined terms and any theorems that we prove. Okay, so axioms, also known as postulates, these are a set of theorems, basically, that don't need to be proven. They're statements of truth. And we assume them to be true, we assert them to be true, we don't prove them to be true. And once we have those, right, the final thing that we do is we prove theorems. And these are all the statements in the system that are true, that can be proven and derived as logical consequences from the axioms and the earlier theorems. And if we have all of these, that's what we call an axiomatic system. Now, there's two types of axiomatic systems. There are or two attributes of axiomatic systems. The first one is consistent. In other words, we would like for it not to contradict itself anywhere. And so one of the big tasks of early geometers in the 17th, 18th, 19th centuries was to make sure that they could provide a set of axioms. Well, let's just say that Euclid's postulates, though they were used for 2,000 years, they were the geometry textbook for 2,000 years, they were imperfect and mathematicians knew it. So other people tried to develop sets of axioms and tried to develop plane geometry in the spirit of Euclid, but with different sets of axioms. And so what they wanted it to be consistent so that everything in plane geometry that's true in Euclidean geometry can be proven from those axioms, and then there's no contradictions. The next thing is a system of axioms is independent if no axiom can be proven as a theorem using the other axioms. Now, Birkhoff and Hilbert are very nice independent axiomatic systems for Euclidean geometry, but we're not going to use them. Why use the school science and mathematic ones when they're dependent? The SMSG axioms are a dependent set of axioms. Well, because what the SMSG axioms do for us is they bump us a lot further forward by stating some things as true that don't need to be proven. For instance, we get the ruler axiom in the SMSG. That means basically that we're getting the real number line. Every time I draw a line in geometry, it has all the properties of the real number line. I know that points are on it at a certain distance. I can find where the square root of 2 away from a point is located and put a point there and know that point is on the line. So all these properties of the real line are in the geometry when I use the SMSG axioms, but I don't have to prove it. In another set of axioms, I would have to prove things about the continuity and completeness of the lines in the geometry. To study the ideas of axiomatic systems, we're going to start with the very smallest possible geometries, these finite geometries. They have a finite number of points and lines. And as we do it, we're going to treat these axiomatic systems. There's only a few theorems you can prove about them. They're not very interesting as axiomatic systems, but they do allow us to get used to using the axioms, the undefined terms, and so forth. So as we go forward, we are always going to have the same 3 defined terms, okay, and the same undefined terms. So we're always going to have point, line, and on as our undefined terms. And the word on, in other words, a point can be on a line or a line can be on a point. Right? It's the idea of intersection. It's an incidence idea where things come together. And those are our undefined terms. For our defined terms, we have intersect. So again, 2 lines on the same point. So we're using words like lines, point, right? We're using the defined and undefined terms to create our defined terms. So our second defined term is parallel, 2 lines that do not intersect. Okay, so I just want to make this clear, especially in finite geometry. Don't get this idea that 2 lines that are equidistant from each other forever are parallel. That's not what we mean. We'll see some rather interesting ideas of parallel in these finite geometries. All parallel means is that 2 lines do not intersect anywhere. And then concurrent, that's 3 or more lines on a single point. So those are the defined terms that we'll use in these finite geometries. So let's look at our first one, the 4-point geometry. So you can see we've got our undefined terms and our defined terms, and we have 3 axioms. There exist exactly 4 points. Any 2 distinct points have exactly 1 line on both of them, and each line is on exactly 2 points. So you can see there's a diagram here to the right. I have 4 points. And notice the reason that I drew this arc out here rather than through the middle. If I go through the middle, it looks like there's an intersection point here that doesn't actually exist in the geometry. Now we're going to have to learn that I have to see a point, I have to see a vertex before I believe a point's there, but this one had few enough lines that I could draw it with no intersections where there weren't actually intersections. All right, and the sorry, let me jump back up. Right, so any 2 distinct points have a line, so you pick any 2 points, right? And there's a line that joins them, right? If I pick this one and this one, this line joins them. All right, so that seems good. And any each line is on exactly 2 points. Okay, so I pick a line like this one, for example, and notice that there's only 2 points on it, right? So any line I pick has exactly 2 points on it. And those are my axioms. So what can we prove? Well, here are some theorems that we can prove. Okay, and these are going to be theorems that you prove. I'm going to prove theorems later down here in Young's geometry, and you will be responsible for proving the theorems in 3 finite geometries: the 4-point geometry, the 5-point geometry, and Fano's geometry. Okay, so in the 4-point geometry, if 2 lines intersect, they have exactly 1 point in common. Okay, so you go back up and you start thinking about what it means to have intersecting lines. Well, this line across the top intersects with this line down the side, and they have 1 point in common. Now, you can't just point at the figure and say that. We're going to have to prove it, and we'll talk about how to do that. Again, I'll do the proofs of Young's geometry so you get some insights into how that would work. The 4-point geometry has exactly 6 lines. Okay, well, 1, 2, 3, 4, 5, 6. But you can't just point at the model. The model is drawn after you know all of these things are true. All of these things can be proven without relying on the model. And you see there are some other things. For example, every single line has a line that's parallel to it. Okay. Well, notice which line is parallel to this one, right? What does parallel mean? Parallel means doesn't intersect. Well, this one intersects, this one, everything around the square intersects with this diagonal. So the line that's parallel to that diagonal of my square is this arc around the outside. So those don't look parallel in any Euclidean geometry we've ever seen. They wouldn't be parallel, and you wouldn't even consider that arc a line. But there you go, just trying to explain that in finite geometry, we really are just looking at the points and the lines. They're finite, and they have different looking properties than these definitions may seem like they mean to you. And then prove that there exists a set of 2 lines in the 4-point geometry that contain all of the points. Well, okay, we just had them. I shouldn't have erased that, right? I have this line, which will contain these points, and I had this line. There are others you could choose to make sure that you contain all of the points. So that's what we're talking about. They're not hard theorems, and we're going to talk about how to prove these things are true just based on the axioms. The 5-point geometry is very similar, has the same undefined terms, defined terms. The axioms are almost identical, except, oh wait, I'll have to change this in the notes. This word is supposed to be 5. There exist exactly 5 points. And you can see them over here. Any 2 distinct points have a line on them, so the line actually connecting these 2 is this arc around the outside. Again, trying not to put any extra crossings in there that look like they might be points in the systems. And I was supposed to change the word 4 to 5, but that's the only difference in these axioms. Hopefully by the time you watch this video, I'll have this fixed. So that's the 5-point geometry. There's not a ton of theorems with this because it's so similar to the 4-point geometry. But I would like you to think about this. This is something you should prove or disprove. Does there exist a set of 2 lines in the 5-point geometry which contains all of the geometry, all of the points in the geometry? And then if you disprove, you have to change this word in bold to make it true. Okay? And also you should decide how many points there are in that geometry and prove your conjecture. So those are the simplest ones. The next one is really interesting. So Fano's geometry, named for Gino Fano, and it starts the same way. We have the same undefined terms and defined terms. Parallel, intersect, and concurrent. Oops, I've got a typo there that hopefully by the time you look at this on the textbook here, that we'll have this fixed. Point, line, and on are undefined terms. Okay, so now notice, and let me scroll down just slightly so you can see the model while we're looking at this. So there exists at least one line. That's interesting. We don't even start with points. We start with a line. There are exactly 3 points on each line. Not all points are on the same line. And so that kind of makes sense. You're like, okay, so now I know there are points, I know there are lines, and there's more than just one line worth of points. So here are the two that are really important. So on any two distinct points, there is a line that connects them. So pick any 2 points in the geometry, there has to be a line connecting them. Which line connects these? Well, this circle is a line that connects these midpoints of these sides. I've drawn it as an equilateral triangle. You'll see other people draw it slightly differently. But this circle is a single line. There is not a point here where this looks like there may be an intersection. There's not a point here or here either. Okay, so the last thing we know is that there's at least one point on any 2 distinct lines. Okay, so pick any line that you want. So let's pick this one. And let's pick this one, right? Well, there is a point that's on both of them. Pick another line. I can pick this line here and this line here. And notice there is only one. These look like they intersect a lot, but the only point that's actually on both of them is this point over here. So you can see that there's at least one point on any 2 distinct lines. Any 2 lines you pick, there's a point on them. So what does this mean about lines that are parallel in this geometry? That's something to think about. So finally, we're going to talk about Young's geometry. So Young's geometry is just slightly more complex than Fano's. Again, starting the same way. And, oops, sorry about that. Oops. All right, so these axioms are exactly identical to Fano's geometry, except for this one. So axiom 5 changes. And what is the change? Well, this looks very much like a parallel axiom, right? For each line L and a point not on it, there exists exactly one line on that point that is parallel to L, right? So we have a parallel condition. All right, so let's scroll down a little bit and take a look at this geometry. Okay, and so again, these things that look like intersections are not. Those are not points. The only points are these green ones that are highlighted in the figure. And so there are several theorems we can prove. I'm going to go over these proofs for you. There is already a video out showing you how to create this graphic up here, and also proving the first theorem in Young's geometry, that there are at least 4 points in the geometry. So this is interesting. We find out that every point is on exactly 4 lines. This is an important technique. When I want to show that every point is on exactly 4 lines, the way that we usually do that is we get at least 4 lines on each point, and then we assume there's more than 4 lines and find a contradiction. All right. So that's why I split it up into 2 different theorems here, because again, usually how we prove this single theorem is by doing 2 parts. You'll see that that happens down here. Young's geometry contains exactly 12 lines. Well, the hint is to do exactly what we did, right? Prove a single theorem first, which is that, hey, there's at least 12 lines. And then let's prove that no more than 12 lines exist. And the same thing with the total number of points. So to recap, I'll be proving the theorems in Young geometry and posting them, and you in your groups and teams will be proving the theorems in the 4-point geometry, 5-point geometry, and Fano's geometry. So before we end our talk about chapter 1, the foundations in finite geometry, let's just talk about this searching for a parallel postulate, because it's really interesting that for 2,000 years people debated the truth of whether they were debating whether or not Euclid's fourth postulate was a theorem or whether it was actually an axiom. And it seems that even Euclid had some questions about it. And so it is kind of amazing that and by the way, Euclid didn't invent geometry, right? He was collecting known facts from geometers, not just Greek geometers. He went to Egypt as well, I believe. And he was basically writing a textbook, collecting all of the works of the people who'd come before him. He did add some things. We're not sure exactly which things in many cases, but he wrote a book, and Euclid's Elements was used as the geometry textbook of choice for 2,000 years. But the problem was this Euclid's fourth postulate, Euclid's fifth postulate, I'm sorry, and here it is with an animation. And it's kind of confusing. That's why I put a diagram in. So he's saying that if a straight line crossing two straight lines, so it's a transversal is what he's talking about, a transversal crossing two straight lines, and makes the interior angles on the same side. So we have angles, interior angles on the same side. And it says that if they're extended indefinitely, they meet on that side where the angles are less than two right angles. Okay, so you can see that when the interior angles on this side are less than 90 degrees, then the lines come together and they'll intersect somewhere down there. Well, that's fine. And lots of people tried to prove that it was prove it from the previous four postulates. It turns out that you can't. And this really important property separates some geometries. We'll be talking about hyperbolic geometry and spherical geometry later, but that's the issue, is that we get a lot of geometry theorems called neutral geometry or absolute geometry without that assumption. Well, just to cover quickly what happened, John Playfair finally came through and he restated Euclid's fifth postulate in a way that mathematicians, in the 17 and 1800s could actually deal with. So this is more the typical statement of Euclid's fifth postulate, or the Euclidean parallel postulate. In a plane, given a line and a point not on it, at most one line parallel to the given line can be drawn through the point. Now, it's weird that he says at most, right? Because we think of in Euclidean geometry, there's a unique parallel. Well, it turns out that that's one of the nuances the Greeks were facing, because you can prove that there are parallel lines without using Euclid's fifth postulate. You can prove that parallel lines exist. You just can't prove that they're unique. So that was a difficulty that they were facing. And so there's two possible ways to change this, right? So if I have more than one parallel line to a given line, that would not be a Euclidean parallel condition. Also, another non-Euclidean parallel condition is that there's no line parallel, right? So there are just ways to change, right, the number of lines that are parallel. So if I have exactly one, that is Euclidean, right? If I have more than one, that's hyperbolic. And if I have none, which is less than one, sorry, this should be greater than one. If it's greater than one, hyperbolic. If it's less than one, that's actually zero. Then it's elliptical. And our best image of an elliptical geometry is a spherical geometry, which we're a little bit familiar with because of the globe, right? The Earth is approximately a sphere. Now, it's not really important except to say that where are we headed? We're headed to where we prove as much as we can without an assumption about the parallel condition. And then at the convergent point, so you'll see this neutral geometry section down here is proving everything that we can prove without a parallel condition. Then we assume the Playfair postulate and launch into Euclidean geometry. And these notes aren't complete. There may be a couple of extra sections there by the end of the semester. but that should do for the first 2/3 of the semester or so. All right, so that's kind of an overview of where we're going. The final thing is that Hilbert came up with this idea of incidence axioms. He actually had several kinds of axioms, and all of the axioms are listed here. Axioms, and you can go to Hilbert's axioms and you can see that he has some interesting names for the groups, right? He's got incidence axioms and betweenness axioms, right? To try to describe the idea of what it means for B to be between A and C. He also has congruence axioms, congruence for both figures and angles and so forth. So this is a nice formulation because it kind of gives you these groupings of axioms to tell you what it is we're trying to figure out, what we're trying to state to make true in this geometry, and these incident axioms make sense. This is how the points and the lines of the geometry fit together. Well, it turns out that almost every geometry we know of is an incidence geometry, and these things have to be true of it. And so as we return back to our foundations in finite geometry, we will take a look at whether or not they're incidence geometries. And then there's two special types of incidence geometries I'd like to point out. Now, an affine geometry is an incidence geometry that has the Euclidean parallel postulate, where there's exactly one line parallel. We have parallel uniqueness in a Euclidean parallel property. And the second type that we're interested in is a projective geometry. And this one's interesting. It's an incidence geometry that has no parallel lines, in which each line has at least three points. Okay, so you need at least 3 points on each line, and there aren't any parallel lines. Why? Well, the projective geometries really are what they sound like. We can project, say, a map onto a globe, right? That's a projection, and these types of geometries govern how they work, and that's why they have no parallel lines. So those are two that we'll be talking about, and the theorems for incidence geometries are very similar to what we've proved. We won't prove these because we proved basically forms of them in the finite geometry section. But yeah, this is the possible parallel postulates, right? We can have no parallels at all. We can have a unique parallel, right? Multiple parallels. And so that's enough. Just kind of pointing out that this is what geometers did. They came back to these incidence geometries and tried to play around with them and figure out what was true about them. And it's a good place for us to start, a nice little sandbox for us to play in as we start proving theorems. So good luck getting started here on the 4-point geometry theorems, 5-point geometry theorems, and I'll be back soon with more content.